Hi everyone, I am Dr. Chandrasekhar Gauri, Associate Professor of Physics, Sri Shanmuga College of Engineering and Technology, Salem. Today we have discussed about the topic of superconductors. This topic is covered introduction, principles of superconductors, types of superconductors, properties of superconductors, and applications of superconductors. First, introduction. Every material is made up of atoms and has similar structures, like a nucleus with electrons surrounding the orbit. So, what makes them so different when it comes to conducting electricity? Almost every materials can be defined in terms of conducting electricity. Materials which don't conduct electricity are known as insulators. Materials that conduct electricity are known as conductors, and then there is a third kind which is known as superconductors. Here, the materials, when brought down at very low temperature, carry zero resistance and become pure conductors. Superconductors. Superconductors are materials that conduct electricity with zero resistance when cooled below a characteristic temperatures. Also, these materials expel magnetic fields when transitioning to the superconducting states. A normal conductor can become a superconductor when the electrons are paired to cooperate with the material's vibrating atom. The phenomenon of superconductivity was discovered in 1911 by Kamerlingh Unis. Superconductors find applications ranging from MRI machines and particle accelerators. Ongoing researchers focuses on raising the operating temperature and developing new high temperature superconductor materials for various objectives. What makes a superconductor special? It is first of all zero electrical resistance. Second one is the Meissner effect. Zero electrical resistance. Ordinary conductors waste energy because moving electrons collide with atoms, generating heat. In a superconductor, once the material is below its critical temperature, these collisions stop, resistance drop to exactly zero. Meissner effect leads to complete expulsions of external magnetic flux lines from the superconducting interior when cooled below the transition temperatures. Next, principles of superconductivity. Conventional superconductivity is explained by the formations of electron pairs known as Cooper pairs combined with electron phonon interactions are conceptualized in the VCS theory. Cooper pairs at sufficiently low cryogenic temperatures, interactions between conducting electrons and crystal lattice vibrations cause the lattice to distort slightly. This causes some electrons near the Fermi level to become unstable and rearrange into pairs called Cooper pairs. These Cooper electron pairs can move through the metallic crystal lattice without resistance as they do not get scattered by the lattice vibrations. Large scale coherent movement of many such tightly bound Cooper pairs leads to exactly 0 Tc electrical resistance inside the material. The Cooper pairs also induce a weak superconductivity in the rest of the material lattice, further reinforcing the effect through a feedback loop. Uh, the superconducting materials are different classes exhibit superconductivity at different characteristics temperatures. Some that have achieved the highest known superconducting critical temperatures are mercury. It is first superconductors was discovered by Kamerlingh Unis. These critical temperatures are 4.2 Kelvin. Next, niobium titanium alloys. It is used in MRI machines and particle accelerators. Its critical temperatures are 10 Kelvin. Next, niobium tin. It is used in powerful electromagnets. Its critical temperatures are 18 Kelvin. Next, niobium germanium. It is used in NMR spectrometers. Its critical temperatures are 23 kelvins. Next, ceramic cuprates. It is the first high temperature superconductors discovered by Muller. Its critical temperatures are around 92 130 Kelvin. Next, types of superconductors. Superconductors can be broadly classified into two categories based on their critical temperature and magnetic properties. Type 1 and Type 2 superconductors. Additionally, they can be categorized based on their compositions and discovery timeline, such as conventional high temperature and unconventional superconductors. Type 1 superconductors, it's are primarily pure metals and metalloids that exhibit superconductivity at very low temperatures. Below the example, it's below 30 Kelvin. They are characterized by the sharp transitions to the superconducting state and the complete expulsions of magnetic fields. Example include mercury, the first discovery superconductors with the critical temperatures of 4.2 Kelvin. Next lead, and then next aluminum. It is the examples of types 1 superconductors. Type 1 superconductors are limited in practical applications due to their low critical temperature and magnetic fields. Next, type 2 superconductors. Type 2 superconductors are more complex materials, including alloys and compounds that can withstand higher magnetic fields, and they have higher critical temperatures. They allow magnetic field to penetrate in the form of quantized vertices, enabling them to remaining superconducting at higher fields. Examples: niobium titanium and niobium tin. Niobium titanium is used in superconducting magnets for MRI machines and particle accelerators, and niobium tins used in high field magnets due to its higher critical field. Next, higher temperature superconductors. HTS are a class of materials that exhibit superconductivity at temperature significantly higher than conventional superconductors. It is the above 30 Kelvin. They are often copper oxide based or ion based materials. Examples: yttrium barium copper oxide and bismuth strontium calcium copper oxide, ion based superconductors. These HTS materials are particularly promising for practical application due to their ability to operate at liquid hydrogens and nitrogens temperatures, which is more cost effective than liquid helium. Next, unconventional superconductors. Unconventional superconductors do not follow the traditional BCS theory of superconductivity. They include the heavy fermion superconductors and organic superconductors, magnesium diphosphide. Next, properties of superconductors. Superconductors are materials that exhibit zero electrical resistance and expulsions of magnetic fields when cooled below a certain critical temperature. First of all, zero electrical resistance, Mason's effect, critical temperature, critical magnetic field, critical current density, energy gap, persistent current, isotope effect, and type 1, type 2 superconductors. Those are properties of superconductors. Next, applications of superconducting materials. The unique properties of superconductors have led to their use in a wide range of applications across various industries. Below are some of the most significant applications. First of all, medical imaging. Superconducting magnets are the backbone of magnetic resonance imaging. That's all MRI machines. Niobium, titanium superconducting are commonly used in generate the strong, stable magnetic fields required for high resolution imaging. The zero resistance of superconductors ensures efficient operations without significant energy loss. Second, particle accelerators. Superconducting materials are essential in particle accelerators like the Large Hadron Collider at CERN. Niobium tin and niobium titanium magnets are used to create the intense magnetic fields needed to stir and focus particle beams at near light speeds. Third one, energy transmission. Superconducting cables can transmit electricity with zero resistance, significantly reducing the energy losses compared to conventional copper cables. High temperature superconductors like YBCO are being explored for use in superconducting power grids, which good reversionized energy distributions. Magnetic levitation trains. Superconducting magnets enable megal trains to float above the tracks, eliminating frictions and allowing for the ultra high speed travel. Um, it has achieved speeds exceeding 600 km per hour. Next, quantum computing. Superconducting materials are at the heart of quantum bits, that's all qubits in quantum computers. The Josephson Johnson's a device made from two superconductors separated by insulators. Is a key components in superconducting quantum circuits. Companies like as IBM and Google are leveraging this technology to build powerful quantum process. Then next, energy storage. Superconducting magnetic energy storage systems store energy in the magnetic fields generated by a superconducting coil. The system can release large amount of energy almost instantaneously, making from ideal for stabilizing power grids and providing backup power. Scientific research. Superconducting materials are used in advanced research tools such as superconducting quantum interference devices, which are heavily sensitive magnetometers capable of detecting extremely weak magnetic fields. Squads are used in fields ranging from geology to neuroscience. Fusion energy. Superconducting magnets are critical for confining plasma in nuclear fusion reactors such as the ATR projects. High temperature superconductors like YBCO are being used to develop more efficient and compact fusion reactors. Space explorations. Superconducting materials are used in cryogenic systems for space telescope and detectors. For example, superconducting detectors are employed in astrophysics to observe faint signals from distant stars and galaxies. Finally, industrial applications. Superconducting materials are used in electric motors and generators for industrial applications. These devices are more efficient and compact than their conventional counterparts, making them ideal for using wind turbines and electric vehicles. Thank you for everyone.